Let's begin. Hi everyone. So today is our last tutorial this semester, and we'll talk about CUDA and specifically implementing CUDA kernels. We'll cover generally the programming model for CUDA, which was also covered in the lectures by Avi. Then we'll show how to use a library called Namba to accelerate your Python code, and also to implement CUDA kernels directly in Python. And we'll also show topics like thread synchronization and shared memory, which can help you write better or faster kernels. Okay, so let's talk about CUDA. So CUDA is a programming model and an environment that allows you to leverage the resources of NVIDIA GPUs for general purpose computation, usually numeric computation. And it provides many different tools, such as compilers, and it provides an extension for the C language and software libraries for linear algebra and stuff like that, and developer tools. This is generally the model. And it defines, in terms of the programmer, a model that you can use to write code that runs using thousands of threads on hundreds of physical cores on GPUs. Like I said, it defines extensions to C, which allows you to write code for the GPU. But actually, we'll only use Python here in this tutorial, because actually that's also possible. And it allows you to write programs that are heterogeneous, which means you can execute some parts of the program on the CPU, and they run usually sequentially, unless you have a multi-threaded program, but generally. And at some point, they can invoke some code on the GPU, which will run many parallel threads to do some massive parallel work, and the CPU can continue running concurrently. Okay, so generally, like I said, you can start running some program on your CPU, also known as the host, the machine controlling the GPU. It can invoke some code, which we'll call a kernel, on the GPU, which will run in parallel across multiple GPU cores and threads. And the GPU, the terminology here is a device. When we say device, we mean GPU. And at some point, control can return to the CPU. It can wait for the computation to end, or it can continue concurrently. Generally, the host writes data to the GPU memory, or in the DRAM, and it writes code or instructions to execute directly to the GPU. Okay. So CUDA kernels. So a kernel is the terminology that's used in CUDA to specify a function that is called from the host. Again, so host is the CPU, and it executes on the device or the GPU. Okay. So generally, you execute one kernel at a time. This is not exactly accurate. It's possible to actually to execute more, but you can think about it as if they are executing one at a time. It's an easier mental model, because there's a concept called streams, which allow you to queue different kernels. Again, kernels, functions that you want to run on the GPU, you can queue them, and you can define multiple such queues that kernels from different queues can overlap. But generally, in our examples, and usually in CUDA code, you only have one stream, and that means that your kernels do not overlap in time. Moreover, a kernel runs on many concurrent threads. You have to define how many threads exactly you want to use for your kernel. And each of those threads executes the exact same code. So you write your code once for the kernel, and the kernel runs on many threads that executes the exact same code. Okay, so we have this geometry thing, which defines the shape that we think about when we define the threads for the kernel. So it's just a mental model. It's nothing actually physical. So the kernel launches as a grid, which is defined by the user, which can be 1 or 2 dimensional, of thread blocks. And the thread block contains threads, which are, again, arranged in a grid, which can be 1, 2, or 3 dimensional. Okay, so we have a grid of blocks, and each block contains threads in some configuration. So for example, here is a kernel. This kernel was launched with the configuration of 1D, a 1D grid. So each number here is a block, and inside the block, it's kind of hard to see, but there's a drawing of multiple threads inside. Okay, and here this is a second kernel with a 2D grid. Okay. So threads that are within the same block, they have special methods to communicate with each other. They can synchronize and they can share memory. And otherwise, if threads are not within the same block, they can't synchronize at all. These blocks can be scheduled at any order. And moreover, each thread has a unique ID that you can calculate for that thread that specifies that thread's ID in the entire grid. Okay, not in its own block, also in the entire grid that was scheduled, launched with the kernel. So the unique ID, as you will see in our examples, is mainly used for either selecting what data this thread will work on, or for controlling the control flow. So different threads can do different things since they're all running the same code, but they can decide to do different things based on the unique ID. Okay, so again, the multidimensional grid thing and blocks is just for convenience. It's a mental model that helps you work with 2D and 3D data. It's not really, nothing really changes. You can actually implement everything with 1D grid and 1D blocks, but it helps you kind of do specific calculations. Again, we'll see examples in the sequel. Okay, any questions so far? Yeah.
Each kernel can run on several blocks.
Yes, the kernel is the definition of how many blocks you have in your grid and how many threads you have in each block, and the code. Okay, so that code will run as this grid. You can share memory only within the block. Yes. Threads that are within the same block can share memory. We'll show that in our examples. Okay, so how is the kernel actually implemented? Again, it's basically implemented just as a C function using these special extensions for the C language that CUDA provides you. So they have this modified extensions with a special syntax that allows you to define a kernel and its geometry when you launch it. And they have this a special compiler for CUDA which separates the code for the device and for the host and compiles them separately. So this is the only part where we're going to see C code, is just to show you that you can define a function, this global specifier, which is a function that's, again, it's called from the host, executes on the GPU. This is your kernel. Or you can define functions that are only compiled for GPU or only compiled for host. And when you invoke your kernel, you have this special syntax where you have to define the dimensions of the grid. So here we have a 2D grid with 100 by 50 blocks. And each block is a 3D shape of threads in this invocation. So we'll do everything from Python, but it will be very similar. We'll have to invoke our kernels with this definition of the geometry for our threads. Okay. So let's talk about the GPU threads just briefly. As you remember from the lecture, where Avi went into this much more deeply, you have practically zero overhead, as opposed to regular threads which you know from systems programming on the CPU, where usually you have overhead for scheduling and switching and context switching. So GPU threads do not have this high overhead. They're very lightweight, and that's why the main practice that's used is to launch many threads, many more than physical cores. You oversubscribe your physical cores with threads, and the idea is because switching is so low latency, when a thread is blocked due to reading from memory, it's instantly swapped out with another thread that can run because its data is already fetched. Okay, so you can hide the latency for memory just by oversubscribing your cores with lots of threads. Okay. And you can get performance benefits even with very, very trivial kernels just by using lots of threads. Each thread operates on a small part of your data. Okay. Now, to determine the unique thread ID, like I said, every thread has a unique ID which allows you to select the data that you want to work on and also use it for control flow. You have these special variables that are provided by the CUDA runtime. This grid dim, which just tells you the dimensions of the grid. So again, the grid is in blocks, one or 2D grid of blocks, and the block dim, which is the dimension of each of those blocks in threads. So it can be 1, 2, or 3D for all the blocks. And again, you have special variables for calculating the unique ID of the thread inside a block. So block IDX is the index of the current block for the running thread within the entire grid, and the thread IDX is the index of the current thread in the block. Okay, so you can use those to calculate. Let's see an example. So how can we use those variables to actually obtain the unique thread ID? Okay, so we have this grid. So in our grid we have 3 blocks. In each block we have 5 threads. So everything here is 1D. Okay, so this is the block IDX, block index. And block dim is 5 because we have 5 threads in the first dim of the block. We only have 1 dim here. Okay, and the thread IDX is 0 to 4 in each block. But if you want to get a global thread ID, okay, we can just take the current block IDX times the block dim, number of threads, and add the current thread ID in the block as an offset. Okay, any questions about that? So you get a unique ID for each thread in the entire grid. Good. So keep this in mind because, again, this is what we're going to keep using again and again in the examples. So the key idea here is to write a simple program that looks single-threaded, but you have this thread ID as your parameter, and you use that thread ID to select some of the data. And together, when you launch many of these simple threads, you can cover the entire data set. Okay? And this automatically scales to all the available physical processors if you define enough threads. So let's talk about the model here for the scalability. So a key feature is that when you launch a kernel, it scales to different devices. Doesn't matter how many physical processes there are. The rules of scaling are the same and they're very simple. So you have a single thread that's executed by a single CUDA core. And a thread block is executing on one streaming multiprocessor, or SM, which is composed of multiple CUDA cores. So your device has some number of these multiprocessors. Every device has a different number. And your entire grid is executing on the device as in general. So the blocks of the grid are divided onto these multiprocessors. Okay? And the hardware automatically schedules each block on any available multiprocessor. Okay, so let's see an example. So let's say you defined your kernel as 8 blocks of threads. And so if you have a device with 2 multiprocessors, the device will first schedule the first 2 blocks, and then another 2 blocks, and so on. So these blocks are scheduled on the first multiprocessor, and these will be on the second. And if you have a device with a different number of multiprocessors, then you can run more blocks concurrently. So you can define the same kernel definition, and it will automatically scale to more multiprocessors if you have a better device, or less. Okay, that's the basic idea here. Okay, and the last thing that we need to recall from the CUDA programming model is the hierarchy for the memory. So we have a few types of memory available for each thread. We have the registers, which are used for local variables. You can access them per thread. They're only for the thread, and they're extremely fast access because they're on chip. Okay, they exist until the thread terminates, just like a local variable that goes out of scope. And you also have thread local memory. So this stores, again, local variables, but if you don't have enough registers. Let's say you need lots of variables in your kernel function, then they might spill over into the thread local memory, which is actually located in the DRAM. So accessing it is slow. Okay? And it also persists until the thread terminates. So basically, if you have a thread, the first two types of memory is the registers and the local memory. Okay? And the next level is for an entire thread block, you have shared memory, which is also on chip. Remember that a thread block executes on a multiprocessor, and the multiprocessor has dedicated memory for these shared memories for each thread block that's executing on it. Okay, so this is also very fast, and we'll see later an example of optimizing using this shared memory. And it's persistent until the block terminates, so all threads in the block terminate. And the final level of memory is the global memory. This is the DRAM of the GPU device. It can be accessed by any thread in any block at any time, and even by the host. So this is what you use when you copy memory to GPU and get memory back from the GPU. But it's very slow compared to the registers and the shared memory. Okay, and this actually persists for the life of the application, even across multiple kernel launches. Okay, so you can copy things to a GPU, then launch multiple kernels that will read and write from that global memory. Okay, so just some rules of thumb for the kernels. So how many blocks do you need, basically? Well, let's say we have some number of SMs or yeah. No, it's not on DRAM. Yes, this is thread local memory. This is memory for local variables that cannot fit in the registers, so they spill over to the DRAM. So this is what happens if you just define variables and don't say where you want to put them. So they will go to the registers first and then to the local memory. If you want to optimize, then you can specifically state that some of your data will be in the shared memory. Again, we'll show an example later. And this is much faster because this is on chip. Okay, so some heuristics. So again, a thread block is executing on a streaming multiprocessor. You have multiple of these SMs. So you want at least one block for each SM. So everyone is occupied. All of them are occupied. But sometimes your blocks will get stuck because they're waiting for, let's say, data. So you want to have more than one. So when the threads of one block are blocked, then the device can schedule in another block. But let's say if you upgrade hardware, you will have a device with more SMs. So generally, you want even more blocks than that. So the idea is that you should have many blocks. And threads, with the threads, you actually have some more trade-offs. If you have, like we said before, if you have lots of threads, then you can hide memory latency, because the moment a thread is blocked because it's waiting to read something, a different thread can be scheduled. But the threads share the shared memory and the registers. So if you have too many threads, you will exhaust them. You will start moving more memory to the DRAM instead of the registers. Okay. So and there's also this warp size thing that was explained in the lecture, which is a number of threads that are actually executed together. They're scheduled together. There's these groups. So we usually take a multiple of warp size, which is usually 32. So we can say that the typical selection for a number of threads would be something that's a multiple of 32. So threads per block usually is in this range. And if you have a very big data set, then you will still have, let's say, 512 threads per block, but you will have thousands of blocks. And the blocks can be scheduled and queued on the SMs. Okay. Oh, okay, so let's start with the implementation part, unless there are any more questions about the mental model or programming model. Okay, so now that was kind of abstract. Now let's see it in code. So the first thing that we're going to use is a library called Numba. And let's explain it a bit, because it will really help us to do everything in Python here. So Numba is a very interesting and cool library. It's a just-in-time JIT compiler for functions. And it's aimed at numerical code. So you can use it to really accelerate your Python code. Take a Python function and generate machine code from that function, which is efficient and type specialized. And you can run it basically today on any OS, and it supports multiple processors, including NVIDIA CUDA. So we can take our Python code and compile it just in time, which means when we call it, directly to CUDA code. Okay, so like I said, just in time means that when you first call a function, it is compiled and it's saved in some cache. When you call it later, the cached version of the machine code will be executed. Okay, so this is actually what's allowing us to run everything here interactively in the notebook. You won't actually see the compilation, but it's happening. And I can actually update my code in the notebook, and it will be recompiled, and I can run it again. So it's pretty cool. It's a function compiler, so it works directly on Python functions. You don't compile an entire application to some executable. You compile a function to some sequence of machine code. So it does not replace the Python interpreter. You still can run your Python program, but when you call a number compiled function, it will execute the compiled machine code instead of using the Python interpreter. So it's fast. And it only supports a subset of Python. You can't use everything. You can't use all the different types in Python. And you can't use all the different statements, but it supports most things. And when you're writing kind of a numerical code with lots of computations and loops and stuff like that, it works really well. And it also supports NumPy arrays. And type specialized means that it generates specialized implementations based on the actual types that you pass to your functions. In Python, everything is dynamically typed. Here it will infer the types from your call and then generate code based on the inferred types. So this is just a diagram. I won't go into it. The interesting thing is that really after it compiles and transforms it to an intermediate representation, and then compiles it to machine code, you can see it's actually cached. The machine code is cached and executed. Next time you call it, this whole flow diagram won't happen. It will just be in the cache, and you will have a function to run. So let's start using Numba. First on the CPU. Right, let's import. So let's start with a very simple, trivial hello world kind of example. We'll write a function that increments an array by 1. And we'll do it very, very naively by taking an array A and looping over its elements and just adding 1. Okay, so if you have been programming with Python at all, you know that this is not the way to do it. This is a very bad idea. Python is very slow for these kinds of things. But the fact that we use this decorator around our function will mean that when we call it, it will be JIT compiled, and then the compiled version will be run. Okay, so you can see that this variable inc_GPU is not a regular function pointer. It's now a pointer to this callable class called CPU dispatcher. This is what happened because we used this decorator which wrapped our function with this class from Numba. Okay, sorry? It will keep the loop, but it will actually run as machine code, not interpreted Python. Okay, and there's this no Python option that I used, which is basically usually what you want. It means that it will try to compile the whole thing and not use the Python interpreter at all. There's this intermediate mode where it can only compile the tight loops, and the rest of the function will be interpreted with Python. But that's generally not what you want. And if you use no Python true, it will give you an error if it can't compile it to the faster version. Okay, so let's create lots of elements, 1 million elements in an array. And I'm gonna run this function first. I'm taking this pyfunc property from the wrapper. So this would be what would happen if I didn't wrap it. Okay, if I didn't use Numba, and I would run that naive loop using the Python interpreter. This is the performance that I would see. I'm using this magic from the notebook called TimeIt. This actually just runs it multiple times in a loop and gives you statistics of the runtime. So it's very slow, and you can see that on average it took 3.2 seconds to go over 1 million elements in Python with an interpreter. Okay, that's what you expect. basically, very, very slow. Okay, so again, we took the original function. This is basically without number. Now, if we just call it directly, then it will call it through the wrapper, which means it will first compile it and then run the machine code version. And again, I'm using the same time, so now it runs in 270 microseconds. Okay, so that's like 5 orders of magnitude, and all we had to do was add a decorator to the function. It's much faster.
Same number of cores, both versions?
It's single core.
Single core.
Yeah, nothing here in Numba is multi-core unless you specify it specifically. So what happened here is that you're not running an interpreter that interprets every iteration of the loop. Okay? Okay, so that's what happened. And just for fun, let's compare it to NumPy. So npadd gives us about the same performance. So this is npadd, which is implemented underneath with efficient C functions. You get the exact same performance. So this is nice. Okay. And something to note here that the first time you call it, you have an overhead for the compilation, and after that, you don't have the overhead because of the caching. But the reason this benchmark is okay is because the time it thing runs multiple different runs, and it returns in each run it runs a loop, let's say of 1,000 or 100 times, depending on the runtime, and it gives you the best run. So if there was an overhead in the first run, you'll get the best result from the other runs. So this benchmark is actually legitimate. Okay, so now that we have seen Numba, like I said, Numba allows you to compile also to GPU. So now let's use it to compile to GPU. Okay, so we can import this CUDA module from Numba, and it shows me that I'm on the server I'm running on. I have this GeForce GPU, which is supported. Great, so I can start writing CUDA kernels in Python with Numba. Okay, so again, our hello world example was just to increment all the elements in an array. So let's do that as a CUDA kernel. So we have this Python function. We wrap it with CUDA JIT this time. Okay, same idea. But now we have some extra things from this CUDA module. For example, the thread IDX and block IDX special variables, which, as you remember, allow us to calculate the unique ID of the current running thread. So this will run on the GPU after it's compiled to GPU machine code. And these will translate to the thread unique ID. So I'm computing taking the offset of the thread in the block and then calculating taking the number of threads per block and times the ID of the current block. So this gives me the global ID of the thread. And now my actual calculation. So I calculated an index of the thread, and now I actually don't have any loop. Okay, there's no loop here. So why is this? I'm assuming that I will have more threads than array elements. So if my array has a million elements, I'm assuming I will create a grid with more than 1 million threads. So each thread will correspond just to one element, and it will just directly increment it. Okay, so I ran that. So now I will define my block size. So this is the threads per block, and the grid size, I'm just calculating it based on the block size, so that I have a total number of threads that exceeds the number of elements in my array. Okay, so I have lots of blocks, as you can see, but 256 threads per block. Okay, now I will take my array, copy it to the device, to CUDA, to the GPU, sorry. This will copy it to the GPU DRAM, similar to what you do in PyTorch. And now I'm actually invoking the kernel. So it's similar to what you saw in the example snippet of C code I showed you, where you have to invoke the kernel with a special syntax defining the size of the grid. So here you invoke your function. So this is the wrapper for the function that will JIT compile it. You specify the grid size and the block size, and you provide the arguments. Okay, and this last thing is synchronized with CUDA, which will wait for the kernel to complete before it finishes. So it will time the whole thing, including the synchronize. Okay, and finally I will copy it back. So let's run that. again, I'm running here a grid with more than a million threads, which each thread is only doing a simple operation of incrementing the element. Okay, so we got better performance. If you recall, it was about 250 microseconds before with the CPU version. So now it's still very fast, even faster, because everything is happening in parallel. So nice. So that's the first version of the naive kernel. And the important note here is the synchronized thing. Why we need it for the benchmark. Notice that I had to synchronize here. If I hadn't synchronized, do you have any idea what would happen? No, it's not a race condition. Think about the first slide where I said that CPU can run concurrently with the GPU. So basically, it waits for the current kernel to end, because if you don't synchronize and you just launch a kernel, and specifically also the data is already on the GPU, then it's non-blocking. It returns immediately. The kernel is executing on the GPU, and then you can execute another kernel immediately. So you don't know if it ended. If you want to measure the duration of the kernel execution, then you have to wait for it to end. Otherwise, you return immediately, and you can execute another kernel. So it's important to understand this. Okay, it's non-blocking. But there's a nuance here that if you copy memory from the host, it is a blocking operation. If you remember, we manually copied. But here, if I invoke my kernel with A, not the device A, so this is A in the host memory, then Namba will automatically copy it to the GPU. So now, if I run it like that, then I'm not. I'm actually adding the overhead of copying. Okay, so that's why it's much slower. Okay, I have a copy of the input and the output back. I had to copy the A to the GPU, and then I had to copy it back to the host to get my result. Okay, so that's why I don't need to synchronize here, because there's this implicit synchronization due to the copying. But it's much slower because I'm measuring this overhead for each invocation. So this invoked 100 times for each of the 7 runs. So I had this 700 time overhead of 2 copies. Okay, so let's talk about the dependence on input size. We got performance with that trivial kernel, but we had a major limitation. So remember that we had to have more threads than the number of elements in the array. Okay, so this is actually a limitation. Usually you don't want that. You want to be able to process all the elements, even if you define a smaller kernel. Okay, so we don't want our grid to depend on the input size generally. It's not very convenient to do that. So here's an example. If I have the same million elements, but I run it on a smaller kernel configuration, and I increment, you can see that some elements in the end are not incremented because there was no thread with an ID high enough to reach those elements. Okay, make sense? So how can we fix it? So basically, the pattern is that you allow a thread to process multiple elements, but you space them apart very widely. So you space them apart with a very big stride that jumps over the entire grid. So only if you have data after the last thread in the grid, you will see that data with the current thread. Okay, so that was abstract. Let's demonstrate it. So here I have another kernel. This is a kernel that multiplies 2 arrays element-wise. So I have this kernel, again, wrapping it with CUDA JIT, so it compiles to the GPU. I have these 2 arrays. Okay, I'm calculating the unique thread ID, again, like before. But now I'm doing an extra thing. So I'm saying I want to go over multiple elements. I'm starting from my unique thread ID. So before we just took the element of that thread ID. Now I'm starting from that. I'm ending when my data ends. I don't want to go over my data, go after my data. But I'm defining a stride that is threads per block times number of blocks. So this is the number of the entire number of threads in the grid. So if I have data after the last thread in the grid, I will actually go there. So I can just loop with this range. Okay. So it's very simple. If my stride takes me beyond the data, nothing will happen. Okay, and I start with the current ID. So this is a common pattern that you can use for decoupling between the size of the data and the size of the kernel. Okay, so now I have again a million elements in A and B. So now I run it with a kernel that has enough threads for each element in A and B. And now I run it with a much smaller kernel, and you can see it still has a result at the end because we use the strides to reach the end of the data. Okay, so let's talk about race conditions. So since this is a multi-threaded environment, if you try to read or write to the same location with multiple threads, you will get a race condition. So you can have a read after write where you try to read something that's not update, or write after write where there's a conflict of two threads that are trying to write the same location, and only one of the writes will be visible. Okay, so let's see an example. Let's say we have a global counter, because so far we wrote to different memory locations in our threads. But let's say we have a global counter, and all the threads have to increment it at some point during their run. Okay, so we need to read, compute counter plus 1, and write back. So at any point here in the middle, another thread might read the wrong value, or compute the wrong value, or write the wrong value. Okay, so this is a race condition, classic race condition. But we can this is something that we can overcome with atomic operations, which are part of the CUDA API. So we can basically have an atomic operation that implements all three steps, and it's guaranteed to be atomic. So no other thread can interrupt you while you're doing that. So I have this global counter as a parameter, and I have one thread that's just incrementing it, and another thread that's incrementing it through this CUDA atomic. Okay, if I run my two threads, you can see if I run the regular kernel, the value is 1. Okay, so it's not what I expected. But if I run it through the atomic synchronization, then I get an increment for every thread that was in the grid. Okay, so that's pretty simple. Let's look at a more useful example. Let's say we have to compute a histogram. Okay, we have an array. We want to compute a histogram. So I'll show you this, and I'll also show you two convenience functions in Numba that allow you to calculate the thread ID simply. Since it's a common pattern to calculate the thread ID based on the dimensions of the grid, you have these convenience functions. So this is a kernel for a histogram calculation. I have a array X. I want to take elements in the range between X min and X max and write them to histogram out. So let's say histogram out has 10 bins. Okay, so I will calculate the number of bins is just the number of elements in histogram out, and the width of the bin is just the range of the data divided by the number of bins. So this is each bin. And now I'll do the same pattern as before, but I will calculate the thread ID based on these functions from Numba. This is a CUDA grid. It gives you the global index of the thread, assuming a 1D grid. Okay, so it just does the multiplication for you. And the grid size is the number of threads in the grid, assuming a 1D grid. Okay, so I have the same idea. So I go over my data with these strides. I calculate the bin number just from the data based on the specific element, and I use the atomic to write it to the histogram at that bin. Okay, I add 1 at that bin. So all the different threads are incrementing different counters in my histogram. So okay, again, let's take 1,000,000 samples. I can run the histogram calculation with CUDA. Okay, you can see I defined the 10 bins, and I got an output. It's a Gaussian distribution, so it makes sense that you have more elements in the middle. And NumPy, you can see, gives you the same result, same idea. So just to compare the performance that we got, let's run it with NumPy and with our kernel. And also I want to show you that here I'm using arrays on the host. So here X is in the host memory, and the output is also in the host memory. While here I'm first copying it to the device, both the input and the output arrays, and then I'm running it. Okay, so here I don't have the overhead of copying. I'm not timing the overhead. So you can see the kind of the difference and the effect of the overhead. Okay, so generally you can see on CUDA, due to the parallel execution here, the results are much better. But if you actually don't pay for the penalty of overhead, you really get much better results.
Don't you pay overall performance for other processes because you are now locking processing units while waiting for a copy? So it's even extra.
What am I locking?
I mean, when you have a process that now need to it locks memory location, but only this process can use it. No one else can use this unit now, this element. So you cannot use another thread that will take context
On the host? On the host, it doesn't block me on the host. I can run more threads on the host if I want. What I'm showing is that the host thread that invokes the kernel has to first copy the data to the kernel, then invoke the kernel, and then wait for the kernel to end, and then copy the data back. So that's this example. And in this example, I first copy the data, and then when I run the benchmark, I'm just waiting for the kernel to end, but I'm not copying. So that's the idea. Okay, so let's continue for the last example of optimizing with shared memory. Okay, so like I said, you sometimes need to cooperate between threads by working on the same data. And we have this global memory, which we use to communicate with the host, but it's very slow. So we don't want to use it, even though it's accessible to all threads in all blocks. And we have this fast shared memory that's only accessible to threads that are in the same block. Okay, and we can actually use it for optimization of performance. So since the classical example, and it's a deep learning course, and all the basic building block for all our deep learning models is matrix multiplication, let's see how to implement it in CUDA. So let's start with a naive implementation and then optimize it a bit with shared memory. Okay. So the naive implementation of a matrix multiplication, we will have multiple threads, again, lots of threads, and each thread will only calculate one element in the output matrix. Okay. So let's say this element is calculated by a specific thread. So to calculate that element, what I need to do, I need to take my thread and read this row from A, and then I need to read this row from B, okay, and compute the inner product. Simple. So let's do that. I have this matrix multiplication kernel. Now I'm using a 2D grid. Again, so this is an example where it's more natural to have a block, a thread block that's 2D, just because then I have two indexes, don't have to calculate them myself. So I have a 2D grid, and each thread will have a 2D index, which I'll use to select the input row and column and select the output element. So I have my index of the current thread, which will also correspond to the output index. Okay, and I need this bounds check to see that my thread is not beyond the data, again, because I will have more threads than data. Okay, and then all I have to do is just calculate this inner product. I'm reading from A, so I'm reading a row from A and a column from B, okay, and writing directly to the output. So remember now, output A and B are in the global memory. So this is slow because I have to read from global memory. This is slow because I have to read from global memory, and this is slow because I have to write to global memory. So I could have actually, instead of out here, I could have first written to a register. Let's say I would add some temp here, temp variable, and then written to that, and finally written out to temp. It would be one possible optimization because that would be in the registers. But I will show that in the other implementation. So let's define our kernel geometry. So we have some n, which will define our matrix dimensions. I will have an n by 2n matrix A, and then 2n by n matrix B. Okay, and this is my expected result using NumPy to multiply them. Okay, I will take the block size to be defined by the warp size of the device and calculate the grid size so that I have more threads than data. Okay, and you can see I have a grid, first of all, a block dimension. So every thread block is 32 threads by 32 threads. And I have 32 by 32 grid of blocks. Okay, so let's run our simple kernel. Okay, I'm checking here that I'm getting the same result that I'm expecting. See that it actually works. And great, so I invoked my kernel with griddim and blockdim. Nice, so nothing very interesting there. But except for the fact that everything happened in parallel, every single element here was calculated by a different thread. Okay, so the whole thing was happening in parallel. Okay, but so we had lots of threads. We had generally lots of parallelism, but why is it actually still not efficient? Think about what I said about the memory. Well, you have to read A and read B. So think about two threads that are in the same row. So two threads that are in the same row, they have to read the same row from A. And two threads that are in the same output column have to read the same column from B. So they're both reading the same data from the global memory, which is slow. Okay, so we have this multiple times reading the whole matrix A and multiple times reading the whole matrix B. So we pay a price for that. Okay, so now the idea is to use shared memory to make it more efficient and reduce this global memory bandwidth. Okay, so remember that the shared memory is on chip and it's available inside threads of the same block. Okay, so we want to take advantage of it. Okay, so how should we actually implement it? We need to define some algorithm that will take advantage of the fact that you have shared memory in a block. So I'm not going to read this, I'm just going to visually explain it. You can read it later if you want. So we want to calculate some output element here. And again, every output element will be calculated by one thread. But we will do it in blocks. So this yellow block defines our block size, or thread block size. So this is each thread block has block size by block size threads. So what we're going to do, we're going to make those threads, first of all, copy memory from A and from B to the shared memory. So each thread will copy one element from this square submatrix in A, and one element from the square submatrix in B. And after all the threads in my block have copied this square from A and this square from B, then I will do the multiplication to calculate part of this element. Why is it part of the element? Because I have the other square here, the next part. So I need to go over these squares on A and on B and calculate every single element here in parts. But that way I will be able to use the shared memory and get better performance. So I have to actually modify my algorithm, take advantage of it. So let's show it quickly. The idea is to have this subarray A and B, which is shape block size by block size. So let's say we have a block size of 32 by 32 threads. So this will be a small chunk of 32 by 32 from the whole matrix A. So I define it like this, shared array. And this is my global ID of the current thread, X and Y. So this is the output element that I want to calculate. Okay? And this is the element of the index of the thread within its own block. So this is the thread ID XX, not the global, but in the block. Okay? And BPG is blocks per grid. Okay, so first, again, if I'm out of the data, if my thread is over the bounds of data, I don't need to do anything. Otherwise, what I'm doing here is I'm going over these square blocks of shape, block size by block size. For each square block, I preload one element. So this current thread, will only take one single element from A and one single element from B and write it to the sub matrix. So the element will be corresponding to its row and column. Okay, then I wait for all the threads to finish preloading into the shared memory. After I have everything in my shared memory, then I can compute part of the inner product. So this is the inner product only on the square part. And I'm accumulating it in my final result for that thread. So the result for that thread will be one output element. Okay, so I'm accumulating that. Then I have another synchronized thread here. Can anybody think why? Wait for the others. Okay, so I need to explain it. So sync threads waits for all the threads in the current thread block. It's a barrier. It will block the thread until all the threads in the thread block reach that barrier, and then it will release all of them. So why am I syncing here? It's obvious. Here it's obvious because I need to fill the shared memory with the entire square. But here, the reason I'm syncing is otherwise this thread would continue and reach here, and then it would fill the square with data from the next square. And another thread might still need it, so I need to wait. Okay, so that's the whole idea, basically. Okay, and now, so I explained this sync threads. You can read it if you want later. Let's run it, see that we get exactly the same result. And we can benchmark it compared to first NumPy's matmul and the naive implementation and the fast shared memory implementation. You can see it really provides a benefit. But in this case, for this size of data, both are actually slower than NumPy. But still nice. Okay, so just to wrap up, we saw that CUDA is actually a very powerful framework that allows you to write scalable multi-threaded code for general applications, whatever general purpose that you want, not just for deep learning. And if you have the right mental model for how CUDA works, then you can really do arbitrary computations with it. You just need to define your computations in terms of the thread blocks and the grid. Okay? And we saw that you can use NumPy to do everything in Python and actually even modify the code and then just recompile it on the fly, just in time, iteratively. And as a bonus, we saw that actually we can also not use the GPU, but just use NumPy to get extra performance by compiling to CPU. So you can really use these tools to speed up your pre-processing tasks like data loading or data augmentation before the input to your model, because usually your model training is already happening on the GPU. But this could really help you get some extra performance when you do end-to-end training with the initial parts. All right, so hope you enjoyed the course. Good luck with the project. Thanks.